Okay, welcome to today's lesson. We'll be exploring the relationship between electronic configuration and oxidation state. How do I determine oxidation state from the electronic configuration of an element? So, first, if you've not watched the video on electronic configuration, you might not understand this, so endeavor to watch that video so that you understand better. Okay, hydrogen, for example, has atomic number of 1. Then this is the electronic configuration. This is the shell configuration as well. The first shell, just like we said, can take 2 electrons. So hydrogen can gain additional electron because it still has space in the first shell, and hydrogen can also lose 1 electron. So the chances are basically the same. When an element loses an electron, it becomes positively charged because the number of protons is now more than the number of electrons. As such, it will make the element to become positively charged. And then if an element gains an electron, it becomes negatively charged because the number of electrons are now more than the number of protons. So that is why you see +1 and -1. -1 means that hydrogen can also gain 1 electron, and hydrogen can also lose 1 electron. Okay, for helium is written as 1s2. It has only 2 electrons in the first shell. It is full, and helium doesn't have a need to gain electrons or lose electrons. So it doesn't gain or lose electrons. So helium is stable, and then it has an oxidation state of 0. Okay, also elements gain and lose electrons in order to become stable. It's very, very important to state that, because empty spaces within a shell leads to certain instability within an atom. So once the shell is full, it confers a degree of stability to an atom. So part of the reasons why they go into chemical combinations. Anyway, so lithium, this is the electronic configuration of lithium, the orbital configuration, and the shell configuration. As you can see, lithium is written as 2-1. It means the first shell is full, then the second shell has only 1 electron. The second shell can take 8 electrons. So in order to be full, lithium needs 7 electrons, need to gain 7 electrons. If it does, it will have an oxidation state of -7. But however, to also have a full shell and be stable, just like I said earlier, lithium can lose 1 electron. So it is easier for lithium to lose 1 electron than to gain 7 electrons. So very, very important. So lithium rather will lose 1 electron than to gain 7 electrons, in which case the valency or the oxidation state becomes +1. For beryllium, the configuration is 1s2, 2s2. So written this way. So even if the second shell is not full, it needs 6 electrons. Beryllium is easier to lose these 2 electrons and have a full shell than to gain 6 and have a full shell. So beryllium will lose 2 electrons. And remember, when elements lose electrons, their oxidation state is positive, so it has an oxidation state of +2. And then boron, similar, 1s2, 2s2, 2p1, 2, 3. Rather lose 3 electrons to have a full shell than to gain 5 electrons. Yes, basically that's how it works. Okay, the same applies to carbon. Carbon has an oxidation state of +4 or -4. It is 2 4. To be completely 8, it needs 4 electrons extra to be stable, and then it can also give 4 electrons to be stable, to be full. So the chances are -4 and +4. So the oxidation state are -4 and +4. However, there are exceptional cases. Sometimes you see carbon with an oxidation state of +2. So carbon takes oxidation state of -4 when it's reacting with elements that can donate electrons, like metals. Metals generally donate electrons. And then it has an oxidation state of +4 when it reacts with other non-metals. In this case, is the one donating electrons. So like I said, sometimes you see an oxidation state of +2 is because of the electronic configuration of carbon. 1s2, 2s2, 2p2. 2 electrons can be donated from this subshell. They are different subshell. So these 2 electrons can be donated from this subshell, and then we still have another subshell. So that is why you have that exception. Most exception that occurs as a result of the fact that some subshells are also stable when they are full. So this 2p is not full, so the 3 electrons can be donated, and then this 2s is full, it's more stable, although the electrons can be donated anyway. So those are the reasons why we have what we have exceptions, or what we call variable oxidation states. It's very important to take note of that. Okay, for oxygen, this is the configuration 2,6. It will be easier for oxygen to gain 2 electrons to become 8 than to lose 6. So in the electronic configuration of oxygen, the oxidation state is usually -2, although exception at times you see oxygen having a -1 oxidation state, basically because of the 2p4. There are 4 electrons, so it can lose 1 and become 3, though 3 doesn't mean it is full. When a subshell is half filled, it is more stable than when it is not full. So half filled or completely filled shells confer stability. The atoms are more stable with that configuration. That is why oxygen can gain 1 electron or gain 2 electrons. Okay, fluorine. This is the configuration of fluorine. It can gain 1 electron, as you can see. P subshell can take 6 electrons, so 1 electron is needed. Here too, the second shell can take 1 electron more. So when it does, the oxidation state is -1. And of course, neon is full. It doesn't gain nor lose electrons, so the oxidation state is 0. So it's the same explanation for all these. Remember, there are exceptions. I expect you to practice the exceptions, because no explanation about the exception at this level will do. As much as you can, practice them. Sodium is +1 because it can lose 1 rather than gain 7. Magnesium is +2, it can lose 2 rather than gain 8, and so on and so forth. Silicon, like carbon, can be +4 or -4 because the chances are the same. And then phosphorus can be -3 I did indicate that here. And then can also be +3 at some point, can be +5. Those are exceptions. Very, very important. Please do take note of them. So the same, especially for these elements I'm mentioning, for sulfur, and then sulfur has an exception of +4 and +6, and then the reason why it is -2 is understood from the electronic configuration of sulfur. So take note of the elements that has exceptions, because we'll be coming across them often at this level. So if you know them ahead of time, it will help you a great deal. Thank you very much.